welcome back to Café con Chemistry. We'll begin this discussion by exploring the concept of dynamic equilibrium and the equilibrium constant. We have previously discussed chemical kinetics, which, as a brief recap, looked at how quickly a chemical reaction occurs. We will be continuing on with chemical reactions. However, we will be focusing more on the extent of a reaction and reaction conditions that affect the final concentrations of both the reactants and products. Up till now, we have primarily written and talked about reactions as if they only proceeded in a single direction. But in actuality, all chemical reactions are reversible, and both the forward and reverse of the reaction can favor one or the other depending on the overall reaction conditions. Chemical equilibrium exists when the forward and reverse reactions occur at the same time with the same rate. It is important to note that at equilibrium, the reactant and product concentrations are constant, but that does not mean they are the same concentration. Eventually, the reactant and product concentrations are constant because the forward and reverse rates have become equal. Chemical equilibrium is a dynamic process because molecules are continually reacting even though the overall composition does not change. For a general reaction, when the system reaches equilibrium, then the forward rate is equal to the reverse rate. We can substitute the rate relationship to give the following, which rearranges to the ratio of the rates equal to the ratio of the concentrations for the products over the reactants, raised to the stoichiometric coefficient. This ratio of rate constants is equal to the equilibrium constant, denoted as capital K. The ratio of the rate constants at a particular temperature is called the equilibrium constant and is denoted by a capital K sub C. Let's determine the rate constant for the following reaction of dinitrogen tetroxide to nitrogen dioxide. This is a relatively simple example because we have only one product and reactant. Remember, the double-sided arrow indicates a reversible reaction. If we have a closed system of solid dinitrogen tetroxide and it is heated, the reaction between the colorless reactant to nitrogen dioxide, which is a red-brown color, can be observed. At the start of this reaction, the initial concentration of nitrogen dioxide is 0. However, as the reaction progresses, there is a decrease in reactant concentration and an increase in product concentration. Eventually, this system comes to an equilibrium where the ratio of reactant to product does not change. The equilibrium constant is a measure of the extent of the reaction and how far the reaction has proceeded. It is important to understand what the magnitude of K tells us about a reaction. If K is small, then the ratio of product to reactant concentration is very small, meaning the reaction produced very little product or there was no reaction. If K is large, then the concentration of products is predominant and the reaction is product favored. Lastly, there is an intermediate value of K where there are significant amounts of both reactants and products and are at equilibrium. However, if you want to measure the relative amounts of product and reactants during a reaction at a particular point in time, this is known as the reaction quotient and is denoted by Q sub C. This differs from the equilibrium constant because it's not looking at the system at equilibrium. The reaction quotient helps determine the direction, either the forward or reverse direction, in which a reaction will proceed, depending on different factors. If we take, for example, the general reaction from earlier and wanted to determine the reaction quotient at a particular point in time, it would be as follows. As you can see, calculating Q is the same as calculating K, but remember, in this case, we are not looking at the reaction at equilibrium. When calculating both Q and K, it is important to mention a few things. When calculating both Q and K, these are ratios, so they are unitless because they involve a thermodynamic parameter called activity. Activity is the ratio of concentrations or pressures of a substance to its reference standard state concentration or pressure. For pure substances, the standard state for a liquid or solid is equal to 1. When writing reaction quotients for heterogeneous systems, We are only concerned for a change in concentrations, and that is why we eliminate the terms for pure solids and liquids. For example, if we want to write the reaction quotient for the following reaction of gaseous carbon dioxide reacting with solid carbon to form carbon monoxide, it would be as follows. As you can see from the equation, carbon is a pure solid, so this will have a value of 1. And the reaction quotient will only depend on the concentration of gaseous carbon monoxide and carbon dioxide. Lastly, if you have elementary steps in a reaction, the overall reaction is the product of each reaction quotient or equilibrium constant for the steps. I know we covered a lot of information, so as a brief recap of the equilibrium constants, we know they are constant at a given temperature. If the temperature is changed, the constant changes for the temperature and does not depend on the initial concentrations. At equilibrium, the reactant and product concentrations are constant over time with the forward and reverse rates equal to each other. The equilibrium constant equals the reaction quotient at equilibrium. Thank you for listening to today's lesson and have a wonderful day. Thank you.